operations, look at the hardware that's applied, look at the sequence of operation, and actually test the hardware to make sure it's operating in essentially as good a new condition. And then the third area is controls. Again, do we have the right smarts in place to control these buildings as precisely as they deserve to be? And I'd like to spend just a couple more minutes talking about controls and walk you through a real scenario illustrating where the energy savings often are and why controls represent a real future opportunity for us. Every building at the core of its HVAC system will have an air handler, and oftentimes it'll have several air handlers. And these air handlers bring air into the building, they'll heat it, they'll cool it, they'll filter it, there'll be a fan that conveys it through all the ducts in the building, and maybe one air handler will serve a specific floor or a specific wing. And for about 2 decades, Stanford has applied industrial-grade control systems at the air handler level, because this is really the primary single most significant energy-consuming system in most buildings. This is actually a very simple screenshot from one of our control systems, and there's a lot going on. I know there's a lot going on, and that's the point. In a typical air handler, we'll have air coming in from the outside. It goes through a filter, it goes through a fan, a heating element, a cooling element, and then it's distributed out through a branch of ducting to the individual rooms. And if you've got air going in, you've also got air coming out. So there's exhaust ducts in the rooms that bring air back to a central plenum, and this gets ducted out, in this case, through a pair of exhaust fans. What's important to note here is all these temperature and pressure instruments and control actuators. It's a lot of information that needs to be monitored and controlled. It's worth it, but it takes some effort, and this is just at the highest level of operation in a building. You take it a step further, and you have all the individual rooms and all the air going into those rooms, and we call that the zone level. And 20 years ago, even 10 years ago, we were putting in new buildings that had pneumatic control systems. Basically, there was no electronics involved at all. You really couldn't see what was going on at the room or the zone level. They were highly effective. They were highly reliable. But as electronic controls became more cost-effective, all new buildings now have electronic controls. The buzzword is usually direct digital control systems. And then you can start to see the actual temperature in those rooms in real time, and you can control the set points and start doing some real precise control. Of course, now we have a lot more data we have to monitor and store. And what do we do with that information? And are we fully utilizing that information to do even more aggressive energy management? So here, this is just one sample floor served by one sample air handler. And each one of these rooms will have an air box, typically in the above the ceiling tiles in that room. And that's what actually controls the final flow and temperature of air going into the space. And this adds another layer of complexity and data to the mix. This is a typical air handler box, and air from the prime air handler will come in this side, and it goes across an airflow element and an airflow control damper, and it goes into the box, and it comes out the other side and eventually goes into the room. In the wintertime, we actually boost the temperature a little bit here with these reheat coils. There's hot water comes through this valve. An air handler typically only heats the air so much, and then these finish the job. Interestingly enough, even in summertime, when the air handler is cooling the space, it's putting out cool air, if you have a room right here with a lot of people and maybe IT equipment in it, and it's cooling just fine, over here you may have one individual in the room, and that individual might be very cold. The air's too cold. So what will happen is this reheat loop will heat that air just a little bit to maintain comfort in that space, and there might be some important research going on in that space. You can't have it too cold. So one of the benefits of having this additional level of resolution, we can see what the flows and the pressures and the valve settings are. We can try to minimize this simultaneous heating and cooling just by having better controls in place. So the future of energy conservation, one of the main points here is there's a lot of data that's out there. All new buildings are going in with these smart electronic controls. We're converting buildings with electronic controls, and there's a lot we can do with that data, and we can do more. We can do further control precision on the individual zones so that what's happening in this zone isn't going to affect this zone over here. And we can integrate the dynamics of the buildings and the buildings collectively. They're a dynamic system, but so is our supply system. And Stanford University is in a fairly unique situation that we've got a full power plant on site serving the buildings. And these are two dynamic systems, and if we can get them in sync, we can squeeze out much more energy savings at the macro level. So with that, I'd like to turn things over to Joe Stagner, my boss, Executive Director of Sustainability and Energy Management, to tell you some more about the supply side.
Good. Thanks, Jerry. So some of you may be aware that when the Office of Sustainability was formed in late 2007, one of our first tasks was to come up with a new long-range energy and climate plan for Stanford. So mapping out how we're using our energy and how we might supply that in the future, and what our options were, and present those options then to the president and eventually the board, and they'll pick something and we'll move to implement it. So we got to work in mid-2008, and we came up with a draft plan by summer of 2009. And that plan, we looked basically at, should we continue using steam-powered cogeneration fueled by natural gas, as we use today? We send that steam to all the buildings through underground pipes, the steam loop, and of course, when the heat's extracted, it collapses back into hot water. That's piped back via the condensate return system to the central plant, where it's heated into steam again, and the process goes, and so we have our steam loop. That system leaks a lot of energy. It has about 14% line loss, we call it, because it's very high temperature, very high pressure, and there's lots of mechanical devices along the way to control temperature and pressure to extract fluid out of the steam so you don't have problems and so forth. And so just the distribution itself loses 14% of the heat energy. And then the fact of making it the central plant is all 100% fossil fuel. If we were to continue that, it'd be really tough to have any greenhouse gas reduction, at least directly. So we looked at a number of options, conventional separate heat and power plants that just have boilers and chillers, and buying our electricity off the grid, perhaps making some renewable electricity on site. And so the option was to eventually do a lot of good with renewable electricity and minimizing the amount of gas by going with this conventional approach. Then we found something more unique. As we got the data from our central plant, all the things Jerry told you about, we could finally see at the large scale. We took them for every hour of 1 year, this year 2008 in question, and we mapped out for every single hour how many BTUs of heat were we putting out to the campus via the steam system, and how many BTUs of heat were we collecting from the campus and throwing away. You say, wait a minute, how could we be collecting heat at the same time we're sending heat out to the campus? Well, we have a chill water system. You think of it as air conditioning, but most of you know, of course, that chilling or providing cooling services to a facility is really just collecting unwanted heat from the facility. So we have this chill water system where we send out water to about 42 degrees, a little bit above freezing, and we send it to the buildings. They put in the unwanted heat they want to cool off, as it were, and then that water comes back at about 56 degrees. And so we then apply energy to transform that heat from one side of a chiller to another side so we can send it out to a cooling tower, evaporate a lot of water, and reject that waste heat to the environment. So when we saw the overlap of that, we said, let's do heat recovery. And so we presented that plan to the president and whatnot, and some of you that were here read in the paper in fall of 2009, campus approves a $250 million project to implement heat recovery. So with that, we got to go ahead to actually start designing the thing. And that's where I'm going to pick my presentation up. So I want to explain the heat recovery thing a little bit more first. Jerry explained that even in summertime, if you have a building and it's 90 degrees outside and there's a certain amount of humidity, you have to take that air in from the outside and you have to cool it. Sometimes you have to cool it down to the dew point to knock the humidity down. And so you might be cooling that air down to, say, 60 or 60-something degrees, and then you want to pipe it through the building. Well, that's a little bit too cold for people. We wouldn't want 65-degree air flowing in here, perhaps, in summer. And so you have the local reheat coils, and so we use hot water to heat that air back up. So we have simultaneous heating and cooling. This shows in the summer and in the shoulder seasons, spring and fall, and in the winter, what a typical daily heat profile for a central plant looks like. This is 24 hours a day, and this is the amount of heat that's coming and going from the central plant. So in summer, you can see at night the cooling demand is lower, and then it peaks in the daytime, as you might expect. And lo and behold, there's a pretty constant heating demand for campus. heat for washing dishes, heat for reheating zone controls to keep air temperatures right, any number of reasons we need heat. And so you can see the overlap area here, the simultaneous comings and goings of heat from the energy plant. So obviously if we could take all the heat in this green area that we're actually collecting via the chilled water system and currently exhausting out evaporative cooling towers, if we could find a way to transform that heat into a usable form, send it back out to the building to help satisfy the heating demand, we might save some energy, save a lot of water too, because we won't be evaporating it. Well, that's summertime. What about winter? Well, while we have a much higher constant heating demand, we still have a significant cooling demand. So we have all this heat we're collecting when it might be 45 degrees outside, and we've currently been throwing it away. So why not collect that, transform it, and help meet that heating load? And you can see the transition in the spring and fall seasons. It goes in between the two. So when you sum up all 8,760 hours of the year, we found that 65% of the total heat collected all year round from our cooling system that's now being evaporated, we could redeploy instantaneously and during that specific hour and use it to meet heating demand, and that it would solve or satisfy 80% of our heating demands. So it's great potential. That's it in scale, and Jerry told you why, some of the reasons that happens at buildings. Here's a good picture of it. These are the cooling towers at the Central Energy Plant, the cogeneration facility, and it might be 55 degrees out on a day like today. And what do you have? You have tons of heat and tons of water going up, rejecting this heat from the chilled water system, and also the waste heat from the cogeneration plant. And it's that heat we hope to capture, and if we're lucky in the end, we won't have any of these on campus anymore. This is a schematic, how I explained to you, of the Central Energy Facility and the cogeneration plant. Put natural gas in, spins a gas turbine, makes electricity and makes heat. That heat and electricity are used in chillers to do the chilling work we described, the underground chilled water loop. And then some of that waste heat from the cogen plant, plus heat that's not waste but is actually created on purpose by the extra injection of fuel, is sent out to the buildings. And again, most of you may know enough by now to know some of the, I'll call it myths about cogeneration. Cogeneration is a very good thing in many applications, but there are a few misnomers about it. The first is that cogeneration is good because instead of having a gas power plant somewhere on the grid where you put gas in and all that combustion after it goes to the jet engine just goes out the exhaust, and we're collecting that, and that's what makes cogen so good. But if you read a little closer and understand cogen a little better, you'll find out that most cogeneration plants actually intentionally in the exhaust ducts right after, it's called the heat recovery steam generator, where you take that waste heat and you make some usable hot water out of it or steam,